So my name's Kurt Rohloff. I'm CTO and co-founder of Duality Technologies. And as Matt just said, or we just said, we're based in, actually half of us are based in New Jersey, half of us are based over in Tel Aviv. So we spend a lot of time in Newark Airport. So we're kind of a strange beast to some level in that Duality Technologies was founded with the vision of this new profusion of data and data collaborations has engendered a lot of challenges related to data privacy and how we collaborate on data, how we share data, how we compute on data with data partners, with ecosystem, with infrastructure in the cloud and whatnot, while also protecting privacy. And we've seen this in a lot of places and a lot of times where, for example, there's all kinds of issues of data leakage, there's all kinds of issues of regulated data industries like finance and healthcare being highly limited with what they're doing and deriving value from data, preventing them providing value from data due to privacy challenges. And so though ostensibly Duality Technologies is really about security and cryptography, we're actually very much heart and soul a data science company and how we can enable analytics on data that is protected and sensitive. And so on one side, we're trying to address this pain point of how we can enable advanced analytics, computation in the cloud, data monetization, model monetization, and so forth, while also addressing this conflicting concern about privacy, regulatory compliance, security, and protecting IP and other kinds of business secrets and things like that. And so our solution is that we have a set of techniques that's been coming out of academia, out of DARPA, the DoD, where I personally came out of, and to enable computing on data while it's encrypted. And it's a bit of a black magic type technology in that you can actually take data, encrypt it in ways that no one can really get access to the data in the clear, but still provide computations on the data itself. And the core technology that we have is something that's called homomorphic encryption. And it's been growing in many different spaces and a couple different areas, but it's enabling and on the cusp of addressing all these very kind of serious issues about data privacy, data leakage, whether it's in healthcare, prison time, for being pushed forward by a number of senators for data privacy issues. We all probably a lot of us are familiar with the Cambridge Analytica scandal and so forth. And going on from there. So it's a deep tech, as we say, but we like to think we have the right team to go do that. I myself came out of DARPA. I've been building this technology longer than anyone else since it was first discovered in 2010. And actually our co-founders include 2 MIT professors, including a Turing Award winner. So we like to say if anyone's going to do it, it's going to be us. At the same time also that we also bring in the data science team formerly from RSA, and our CEO, Lon Kaufman, who's based in Tel Aviv and couldn't be here tonight, is basically ran data science at RSA for many years also, RSA being the security company. And so what we try to do is that the classic kind of approach that people have been using for data privacy is basically try to encrypt everything, lock everything down, keep everything on premise. But the problem with that is that as you start to lock things down more and more, it's really hard to provide utility on data. And generally there's been kind of like this all or nothing kind of approach, zero-sum game of providing a lot of privacy or providing a lot of utility from data, driving a lot of value. And we're basically highly focused on really trying to do both at the same time. Take data, encrypt it, run computations on the data, and get utility from the data also. And so, just to kind of give a taste of what's actually going on, we're probably familiar with a lot of the kind of standard encryption technologies, like AES is a technology called symmetric encryption, which, for example, you can hide information so it can only later be used by you. For example, encrypt data, put it up on the cloud, get access to it later. There's another side of that, public key encryption, which is basically encrypt something so you can send it to someone else and only one person can decrypt it, but not run computation on it. And so we have a set of techniques that we've been commercializing built around a privacy technology called homomorphic encryption, which is basically encrypt data, run computations on it, and then go on from there. And this has long been considered a holy grail of privacy technologies. First discovered in 2009. There's been a lot of theoretical improvements, and the market for it is emerging. Traditionally, there have been a lot of folks who've had challenges associated with slowdown, ciphertext expansion, and a very, very different compute model. But we think we've really cracked it, and I'll give some actual experimental results of what we're actually seeing now. But the higher bit, most significant bit, is that whereas in the old days, it would take, for example, when Homemorphic Crypto was first discovered, it basically took a half hour to run a bitwise AND on encrypted data. We're actually at a point now where we're actually encrypting genomic data for NIH and running full-on genome-wide association studies on encrypted genomic data with sub-second response times. So all very good stuff. There's also some other kind of nice benefits to it in that we're basically built off this set of encryption technologies called Lattice Crypto. If you haven't heard about it, no big deal. You will pretty soon. It's one of the leading candidates for the NIST's public key standard coming forward for the post-quantum crypto. But there are challenges, and one of the reasons that so few people have been able to actually use this technology so far is that it's a very, very different compute model. And the analogy I like to use is that a lot of us have base 10 hardware is what we were born with. 10 fingers bend 10 toes. So you learn how to do base 10 math as a small child. When you went to go to computer science school, engineering school, take your first programming classes, the underlying hardware that we have, our computers, our laptops, our phones, and everything else, the underlying compute device, what is it? It's a transistor, right? So binary math. So we learned how to do things like binary decision trees, binary trees, and whatnot. And we had to learn basically entire new data structures, entire new algorithms to take most efficient use of these compute devices that we're given. And that shift of having to go through different data structures, different types of data encoding, different kind of algorithms has been one of the major barriers of how you do data science using homomorphic encryption, which is what we've cracked at Duality and what we're starting to push forward on. And the kind of the underlying science, underlying data science behind homomorphic encryption is that the underlying compute model basically looks a lot like vector algebra. Vectorized addition, vectorized convolution, vectorized rotations are kind of like the underlying base compute primitives analogous to these AND, XOR, and OR operations that you might get exposed to on a standard RAM-based processor like you might buy from Intel. And so the vision that Duality is pushing forward on is that it's kind of like when you go and buy a chip from Intel. You have a chip, what's it good for? You can look at it, it's kind of a really expensive paperweight if you don't have an operating system or a pile of software to sit on top of that. And so it's kind of like what we do at Duality is that we have this core crypto technology, which is open, and I'll get to where it's actually open itself. We fundamentally want the crypto to be commodity. And the real innovation of Duality is how does one do data science on top of this compute model? And how does one go and take standard data science workflows, scikit-learn, TensorFlow, machine learning models, and even things as simple as regression and basic statistical type analytics, and run analytics on data while it's encrypted. And so what we do at Duality is we provide the tools to do data science on top of this encrypted compute model. And on purpose, we make all our crypto technology, the core crypto operations of key generation, encryption, decryption, everything else open source, so it can be inspected, so it can be trusted. We're in collaboration with a number of other large tech firms who are also working on this kind of technology because we want the core crypto to be trusted, and we want to focus and we want to provide capabilities to our customers for how to do data science on top and provide those kinds of tools, the equivalence of scikit-learn on encrypted data, the equivalence of TensorFlow on encrypted data, the equivalence of how one does data science on encrypted data. And so, what we provide at Duality is that you might come in with some basic messages, ASCII text, JPEG images, piles of real numbers in a CSV file, and we provide basically the wrappers for how one would go and take that data and code it into plain text and then encrypt it into ciphertext, and then take your workflows and run secure computation on the ciphertext in and of itself. Run the computation, churn, and then get a decrypt and decode operation from there also. And there's a lot of challenges with that. And like the real innovation with Duality is, you think about when you learn data science, you probably take a standard textbook like CLRS or these other kinds of standard algorithms books, and what we do is basically take those standard algorithms and basically port them over to run on this very different compute model, and take the data structures and port them over to run on this very different compute model. And this is the core vision and core innovation of Duality, is how you do data science on these very, very different type of operations. Underlying it all, though, is our encryption technology, which, if you're interested in this, want to download and play with it, we have this Palisade open source library, a general C++ library, palisade-crypto.org, and we're a bunch of software engineers like you guys, and so we designed it as a good, lazy software engineers. The best software engineers are as lazy as possible, meaning they make things as modular as possible and reusable as possible. And so we basically try to make it so that data science can run on generic compute devices, whether they be laptops, whether they be mobile devices, or servers. And the history of Palisade in and of itself is that I personally have been working on it for a good 10 years or so, primarily with support of DARPA and the other ARPAs, in collaboration with folks at MIT and a number of defense contractors. And where it's been mostly locked into the space of the US defense community, we've basically been taking out to larger regulated data industries, such as finance and healthcare and so forth. One of our earliest public deployments of this technology has been in support of an NIH initiative to enable privacy-preserving cancer research. And so an example of this is that there's this notion of what medical professionals would call a rare disease. I forget the exact definition, but it's like 1 person in 1,000, 1 person in 10,000 denotes what's actually a rare disease. And if you look at, for example, any one hospital might have one rare disease for any one specific type of cancer over several years. And so this makes it very, very hard for any one set of cancer researchers to really diagnose what's actually going on with specific types of less common cancers. But if you look at all the patients over the entire, for example, the United States, over all North America, over the entire world, there might be tens of thousands, hundreds of thousands of people with any one disease, rare disease. And so the vision is there a way to take data from multiple locations and then enable analytics on data over very large populations, over multiple research centers, so that one can then develop more effective cancer treatments. And so what we've done with support from NIH is to, in partnership with the Dana-Farber Cancer Institute, for example, is to enable cancer researchers to encrypt genomic data over, for example, this one data set that we had was 245 patients with 10,000 SNPs, which is basically, think about it as a very, very large CSV file. And running genome-wide association studies, which is kind of a fancy way of saying logistic regression on this actual data itself, and getting back these results all well encrypted. And so last year there was actually a big competition. There's an annual competition for this. There's actually, I think the next one is going to be in the 26th for 2019, although we're not competing into it. And just to give you a hint about where we are as compared to both the leading researchers in the space, so we did this 245 patient data set on encrypted data in sub-second runtimes. Just an indication of how very real it is right now and how very on the cusp we are of deploying this more broadly. Another use case that we've actually had is that we're actually enabling anti-money laundering and fraud detection over encrypted data, particularly as enabled by Duality Technologies, running in collaboration with the CDA, a consortium of British banks called the Cyber Defense Alliance, and being used also by the Metropolitan Police to enable fraud detection and things like that going forward. So as I say, we're very heavily involved with the regulated data industries, healthcare, finance, and so forth. And so I'm sure there's lots of people from lots of other communities. I'm here with several of my other colleagues from Duality Technologies. And of course, we're about to have question and answer session, but always happy to stick around and have further discussion afterwards. So thank you very much.
that people use is differential privacy. Can you maybe just educate us on the nuances?
So, the arsenal of tools that we have, so to speak, for enabling private analytics and analytics on sensitive data is that there are a number of techniques. Differential privacy is one, which is kind of like a real high-level hand-waving version of it, is that you add a bunch of noise to the data so you can kind of obfuscate the actual privacy-sensitive information. The challenge with that, it actually doesn't work very well if you need really fine-grained analysis as you would, for example, genome-wide association studies. So there are several other techniques such as secure multi-party computing where multiple participants each have a share of the data and they run some sort of joint computation, but it's very bandwidth heavy. And there are a couple other different techniques. And there is a broad set of privacy-enhancing, privacy-protecting analytics technologies, of which homomorphic encryption is one of them, and it does solve some problems nicely. And of course, there's others that it doesn't, but it just so happens to be that this is what we focus on.
Just one quick question from me on business models. So the end was, the whole thing was very interesting, but like the part on it takes a network to secure a network.
Right on.
Is that the core use case of this like data sharing among companies use case, or is there a single player use case where a company like across departments would want to implement homomorphic encryption?
Yeah, there are a number of use cases. This is actually one thing that I particularly find rather exciting about this technology is that it's actually shockingly malleable, and that it enables a number of use cases. I shared a slide briefly where there are multiple participants that kind of kick on their own data and run some sort of joint computations and so on. There are use cases, for example, if a fintech wanted to, for example, sell a model to a bank, right? And the fintech or the bank didn't necessarily want to share their either customer-sensitive information or share the model. We actually allow, for example, the fintech to encrypt their model, send it over to the bank run the model encrypted on their data, get back encrypted results, and then the fintech go provide some sort of evidence of how proficient or how accurate, how good their model is on the bank's data while still doing privacy preservation. Mm-hmm. So it still is a lot of, and so what it does is it reduces friction in markets, makes it easier for participants to collaborate, both in terms of multi-parties, one-on-one type computations, things like that. Another use case that we've been looking at also is this co-marketing, where, for example, an insurance provider wants to market to banks' customers, for example. The banks can provide their data encrypted to the insurance provider can run their actuarial tables on the bank customer data, all while protecting the bank customer privacy, and going from there.
Great. All right. Do we have questions? We have this throwable microphone. All right. Nice catch.
Okay, thanks. This is a naive question, but one of the concerns, for example, in the census, U.S. Census, there's been a lot of political pushback, is that as you do data analysis and you get more granular into, let's say, blocks or very close geographies, you can actually predict who the person is that provided the data, even though you don't have the names. In any way, your encryption, your methodology, is there any way to solve that kind of problem, or is that at all not relevant?
Oh, it's definitely relevant, and I have personally talked with the head of data innovation at the Census Bureau, and I know they're actually running a pilot study with a different set of technologies with internal development right now. The model that we address is, for example, the genre of what we do is to take data and derive value from the data, derive insights. Once you actually have those insights, you can do whatever you want with them. But if the insights themselves, for example, in the use case that you identified, you want to know all of, for example, people from a certain demographic in a certain geographic region, and the population size is 1, and that's your insight. Well, if you share the insight, then effectively you're sharing information about that single individual. And so we can't necessarily, we at Duality do not, for example, protect the insights after they're obtained. We protect the data that's used to derive those insights. But good question, excellent question.
Just one more over there.
Hi, this is really interesting stuff. Homomorphic. I was with CertGo, a PKI pioneer back in the day, and I think this is really exciting moving forward. One question is, I mean, public key encryption has so far, disseminated throughout many different industries. How quickly, which applications do you think might still use PKI, or do you see this ultimately replacing all of it, or is there any trade-off in terms of maybe cost or performance, where this would be sort of for applications where you want to work on the data, not just transmit it securely? So how do you see this kind of ultimately supplanting a lot of the PKI?
Right. So let me kind of tease this apart a little bit. So the underlying crypto that we use is actually a public key crypto system, for one thing. For another, the basic need for PKI infrastructures, for example, e-commerce and things like that's not going away, right? It's just there. It works reasonably well. Amazon's making plenty of money off of it. There's lots of e-commerce being built on PKI and more. What we address, and I think kind of the core value add that we provide is deriving insights from sensitive data, not necessarily a public key infrastructure. Thank you.
All right, on this note, thank you so much. This was terrific. Appreciate it.
Thank you very much. Thank you.